Okay, then
Sì, vado anche.
Yes.
to English. Okay, it's a great pleasure for us to have here Valeria Saggio, but she's Valeria because she was one of my students few years ago, and then she decided to go. You had your thesis was in Florence, if I am.
Yeah, my master thesis was in Florence. Yes.
The master thesis in Florence, and then a PhD in Vienna, where she has done a lot of nice work on experimental quantum computation, and it's a pleasure to have her here today to speak of quantum enhanced reinforcement learning, which is something it's a very, very hot topic, and I'm very well published recently by her. So Valeria, thank you.
Thanks a lot for the introduction, and thanks a lot for the invitation. So I have to say that it's always nice to be back home, even if just virtually. But yeah, so I'm very happy to present you one of our latest results today. And first of all, I want to say that I decided to keep this talk very, very basic. So I would really start with the basics, because I know that there's some people in the audience who maybe don't work with quantum stuff. So I thought of really start with the basics and then go slowly to the result of the experiment. Okay, so as you can see from the title, we have two main fields. We have the field of quantum mechanics on one side and the field of reinforcement learning from the other side. Now, since, again, I don't know how many people are familiar with both of these topics, I will start to quickly describe both of them. So now, if this talk was in present, I would have asked you, what do you think, what is the first thing that comes to your mind if I say quantum mechanics? And since now I cannot ask you this directly, or at least it's not very convenient, I tried to guess, or at least I tried to answer like myself to this question. And so let's see. So the first thing that comes to my mind if I think of quantum mechanics is the famous Schrödinger's cat that I'm sure you heard of. So you have this state, the cat being in a superposition of being dead and alive. Or you may think of quantum state. Maybe you're familiar with this notation. You may think of probabilities. You may think of the quantized energy levels. You may think of Einstein, for example, I think. So with that said, I would really start to give a brief introduction to what quantum mechanics is. And I thought of condensing more or less everything in one slide. So at first I chose this title. I said, okay, let's describe quantum mechanics in one slide. Then I thought it sounded a bit too pretentious. So it's at least what we need to know about quantum mechanics in order to understand this talk. And this will be just enough. So I will start, first of all, with the comparison between classical information and quantum information. So just very simply, in classical information, so in the computers that we use, the unit of information is called bit. And it's a digit that can be either a 0 or a 1. And this is extremely easy to sketch, right? I mean, you just have 2 points, one is a 0 and one is a 1. Now, in quantum information, actually, the idea is completely different. The unit of quantum information is called a quantum bit. It's called qubit. And it's usually represented with this notation that you can see here in this equation. So you have psi is equal alpha 0 plus beta 1, where this notation, if you're not familiar with this, this is the ket notation. It's used to represent quantum states. And this is, so this is how a qubit is defined. So now the question is, okay, so how can I visualize a qubit? Because now it's not a value of 0, 1, but it's a quantum superposition of both 0 and 1. So a way to depict a qubit is this. So this is called Bloch sphere. And as you can see, you can express this coefficient alpha and beta in terms of two angles, theta and phi. And you can represent the bit as a vector lying on the surface of this sphere. And this vector forms an angle theta with the z-axis. And now, as you can see, if this angle theta is 0, then you have an overlap of this vector with the z-axis. So it means you are in the state 0. And instead, if theta is pi, then you go down here, and then you represent a 1. So you have the one state. But now what's extremely important about this is that in this case, as you can notice, we can have the value 0 for theta 0 and the value 1 for theta pi, but we can also have anything in between. So when we talk about qubit, when we talk about quantum information, we have to consider that we have the possibility, we have a continuum of possible values. So I can be anywhere in between. Okay, and this is, so how do I obtain this? By tuning the angle. So I basically tune this coefficient alpha and beta. And this is extremely different, right? This is the main concept in quantum information, because in classical information, we only talk about, we have discrete values. The bit can be 0 or 1. But this is not the case in quantum information. So in quantum information, I really have a continuum of possible values. And this is how we describe a qubit. And now the last thing to clarify about classical and quantum information is that in classical information, we do not talk about probabilities. Why? Because the state is either 0 or 1, so it's 0 or 1 deterministically. And again, this is not the case in quantum information. So in quantum information, we have the state of a qubit, alpha 0 plus beta 1, and we have to talk about probabilities of finding the system in either 0 or 1. Now, if you're familiar with the Schrödinger's cat, you might remember you have this cat in a box, you don't know if it's dead or alive, until you open the box. So as soon as you open the box, it means you are observing the system. You're making a measurement on the system in more technical terms. So but when you open the box and you observe the system, then you find whether the cat is alive or is dead, with a certain probabilities. And in general, these probabilities are given by the coefficients of alpha and beta, which are called probability amplitudes. And if I take the square modulus of these coefficients, I have the probability of finding the system either in 0 or in 1. So you just have to remember that in quantum information, it's mostly all about quantum superposition. Of course, there's other features that we use, but I mean, this is really like a fundamental concept, and it will be enough to understand this talk. So it's really important to understand the principle of quantum superposition and to understand the denotation of a qubit. All right, now I go back. So this was quantum mechanics, just very briefly. But now let's go to reinforcement learning, which is the second field of this talk. Now, again, I would have asked you the same question. So what do you think of if I say reinforcement learning? Maybe now, I don't know how many of you are familiar with this. So I thought of putting some examples in the beginning. So you can think, for example, of the game of Pong, where you have two adversaries who have to block a ball. And then as soon as one fails, then the other one gets a point. Or you can, for example, think of a robot, which has the goal of escaping a maze, for example. So it has to find the exit. Or, for example, just very simply, you can just think of a child who's learning how to walk. And why am I giving these examples? I hope this will be clear in the next 2 slides. So again, I decided now to use 2 slides for reinforcement learning, or at least what we need to know about reinforcement learning, again, in order to understand this talk. So the first thing is, so this is not crucial, actually, in general, this slide to understand the talk, but I just thought of giving you a nice overview of where reinforcement learning lies, just to also give you an idea of what I'm talking about. So in general, we have the field of artificial intelligence, which is the field that studies machines who accomplish some tasks that normally would require human intelligence. Within artificial intelligence, we have the field of machine learning, which is divided in 3 main classes. So the first one is supervised learning, then we have unsupervised learning and reinforcement learning, which is what we are interested in. And now, again, this is not extremely essential, but I thought of also giving you just a very brief example of what these fields are used for. So, for example, in the field of supervised learning, we can achieve, for example, data classification tasks. So let's say we are given some pictures of a cat or a dog, and the algorithm, so the machine, has to be able to understand, to distinguish between a cat or a dog. This is just one example. In unsupervised learning, instead, we have an input. So the input is a data set with some data. And what it can happen is that so the algorithm, so the machine is able to find patterns in this data. So it's able to find clusters. And this can be used. So a famous application of unsupervised learning is, for example, detection of anomalies in data. All right, and then again, what we're interested in is reinforcement learning, which is based on a feedback exchange between two main entities. And now this will be more clear in the next slide. So you have to keep in mind that actually reinforcement learning is a bit different from supervised and unsupervised. It does not really deal with data, but it works on a completely different principle. So we have to consider that we have two entities. One is an agent, which is usually sketched in scientific papers as a cute robot, but I mean, you can think of it as in general a machine, an algorithm, or whatever you like. So, but something that is provided with a task to accomplish, so with a goal to achieve. And on the other hand, we have the environment. The environment is simply the world the agent plays in. Okay, so now so reinforcement learning now consists of three main steps. The first step is that the environment sends a percept, what is called percept, to the agent. This is important because this percept triggers an action of the agent. Now, what does this mean? Again, if you imagine, for example, that the agent has to escape a maze, let's say it can go left or right to find the exit. Let's say that the correct exit, so the correct move to find the exit is, for example, the right path. Okay, so now if the agent goes right, then it means it was able to accomplish the task because it found the exit. So now it will receive a reward from the environment. Okay, so it will get rewarded. As if the agent goes left, actually it means that it was not successful, so it will not receive anything from the environment. And the important thing is that every time that the agent receives a reward, this reward is used to increase the probability that the agent performs well at the next round. So it means that the next time that the agent wants to play, if it goes, now the probability of going right is a little bit increased compared to the probability of going left. And then just by repeating this process for n rounds, then in the end, the agent will maximize the probability of going right, so of finding the exit, so of accomplishing a task. Okay, so, and I hope this is clear. So this is exactly what we mean by reinforcement learning. So there is this learning process of the agent who wants to accomplish something. And this learning process is rewarded every time through this reward mechanism. So thanks to the interaction with the environment. Okay, so now the idea is we have quantum mechanics and we have reinforcement learning. And what we want to do is we want to see if and how reinforcement learning can benefit from quantum mechanics. So the question is now, how do I combine both of them? So I thought of giving you this overview. So I just want to say that this table is not intended in any way to be an exhaustive representation of the state of the art of the field, because there's much more going on. But I just thought that maybe giving you some ideas of what people are doing might be nice. So, for example, what people have done, they have treated the agent classically, but they have quantized the environment. And what they demonstrated in 2018, this is a very nice experimental paper, they demonstrated that it's possible to design new quantum experiments. Or what they also did, they now treated the environment classically, but they quantized the agent. And here they demonstrated, so this was treated theoretically in 2014, and then it was demonstrated experimentally in 2019, that it's possible to achieve a speed up in the agent's decision time. So what does this mean? It means that the agent was able to output an action faster compared to the classical case. And then we have a case where both the agent and environment are quantized, which is what we are interested in, and I will focus exactly on this in this talk. So here, this was again treated theoretically in 2016, and then we demonstrated experimentally a few months ago in a collaboration. So the experiment was carried out at the University of Vienna But this was actually a collaboration also with the University of Innsbruck, Leiden University, and the MIT. So in this case, we show that it's possible to achieve a speed up now in the actual learning process. So it means that the agent needs less rounds of interactions with the environment to fulfill its goal. But now the question that you might have is, what does it mean that the agent is quantum and the environment is quantum? So how do we quantize it? So if we recall the slide that I showed you before, so the working principle of reinforcement learning, remember I said you have percept, then action back from the agent to the environment, and the reward from the environment to the agent. Now, since now we want to go to a quantum framework, what we do is we promote percepts, actions, and rewards to quantum states. So again, now we use again this cat notation to indicate quantum states. So what does this imply? This means that now percepts, action, and rewards can be sent in arbitrary superpositions, because if they are quantum state, they can also be in superpositions. So it means that, for example, the actions can be in so the action can be in a superposition of many actions, the same for the percepts and the same for the reward. So now agent and environment can communicate, so they can send these signals via a channel that is called quantum channel. So a quantum channel is the channel that they use to communicate and to exchange quantum states. All right, so this is the first step. So this is the main idea, the fact that they can create and send quantum superpositions. But what is now the consequence of this? So how do we apply this to get a speed up in the learning process? The main idea, and what you have to remember, is that now correct actions, so the actions that lead to a reward, which are the ones we want to find because we want to be able to accomplish the goal, can be obtained using a quantum algorithm that finds them faster. And this algorithm is the famous Grover algorithm. Now, I'm sure that probably most of you have heard of that, but I also think that maybe some other people might not be that familiar with this. So actually, I thought of explaining this quite in detail. First of all, because it's crucial, it's extremely crucial to understand how the experiment works. And also because in general, this is a very famous algorithm that you will hear at some point, and it's always good to know how this algorithm works. It's extremely famous in quantum computation. So now I will open then a brief parenthesis and I will talk about this algorithm, and then I will go back to see how we can apply this algorithm to reinforcement learning. All right, so let's imagine you still use a phone book and you have phone numbers of some of your friends. And in total, let's say that you have n friends, so you have n phone numbers. And suppose that you want to find the number of your friend Mike. Okay, so how would you do it classically? I mean, normally, you would start from the first one. You check whether this is Mike's number. It's not. Then you keep going, and then you still check, and then you keep going and going until you find Mike's number. All right, so once you find it, you stop. So that means that since Mike's number could be just in the beginning of the list, it can be at the end, it can be anywhere. It means that on average, you need n over 2 trials before you find what you're looking for. So that means that classically, which is normally how you would look for a number, you have n, like on the order of n trials before you find this number. But now let's see. Now let's say that I want to use quantum mechanics to look for this number. So how would this work now? Now I can access all of my friends' numbers in a quantum superposition, and this is extremely crucial. Again, I said this in the beginning. It's mostly all about quantum superposition. So I start with a quantum superposition of all the numbers of my friends, and now we can show that if I use this starting point, I can now use only in the order of square root of n trials to find the number. And this is a huge improvement. I mean, imagine you have 100 numbers. If you play quantum mechanically, you only need 10 attempts to find what you're looking for. This is extremely interesting. Now, I know that it might not, I mean, no, for sure, it's not it's not clear why I get this square root of n advantage. And this is what I want to show you in the next slides. So now I would get a little bit more mathematical. So let's start again. I have a database, an unsorted database of n elements. So I have x1, x2, so I have n elements. And let's say that the element that I want to find, which I call target element, is, for example, the element x2. And x2 becomes my win state. Okay, so I represent it by the win ket. So as I said before, I can prepare a superposition of all the elements. So it's the superposition that I showed you before. It's the superposition of all the numbers of my friends. So it's a superposition of all the elements that I have in my database. And this is my initial state. This is the starting point. And now what is useful to consider in this representation is also the state orthogonal to the target element. What does this mean? It simply means that the state orthogonal to the target element is the state that contains all the element that I have, but x2. So as you can see, x2 is not included in this superposition. So it means that I can start with from the initial state. I identify one element that I want to find, x2, and I identify all the other elements that I don't want to find with the loose state. So I can also now represent this geometrically in a plane. So I have two axes. One axis is the win axis, and the orthogonal axis is the loose axis. And I can represent this initial state, this vector S, as a vector in this plane that is arbitrarily close to my loose state and forms an angle theta with the loose state. Okay, now the main idea, since I said I now want to find the win element, so I want to find the x2. What does this mean? I mean that I start from here and I want to be able to rotate this vector in this direction until I get closer to the win state, because that's where I want to go. And how do I do that? Exactly with the Grover algorithm, which consists of mainly two steps. The first step is I have to apply a so-called oracle to my initial state. And as you can see from the sketch here, the effect of applying the oracle is to have a reflection of the initial state of this vector about the loose axis. So now I'm here. So this is my new state, of course, by an angle theta, which is the same as this one. And if you do this mathematically, I mean, you cannot do this now, so you have to trust me on that. But you can see this mathematically, that the effect of applying this oracle to the initial state of doing this operation is of having, again, the superposition of all my elements. But this time, the sign of the win element is flipped. And this is extremely important. So the oracle is used to identify the element that I want to find, so the win state. And how does the oracle identify that? Just flipping the sign. So now this win element is the only one that acquired a minus sign. And this is the first step. Now the second step is to apply a so-called reflection, R, around now the initial state S. So you see that now the reflection is by an angle 2 theta, and this is the final state. And again, you have to trust me on that. This is what you get if you do the math. So what you get is that all the amplitudes are now n minus 4 divided by n square root of n, except for the amplitude of the winning element, which is now this one. So now what you can see is that this amplitude has increased with respect to all the rest. So the other amplitudes now have decreased, and this one is now increased. What does this mean? It means that now I increase the probability of finding x2, right? Because this is bigger. And again, I can see this geometrically because I pushed this vector closer to the win state. And now, so this is in total, this is one Grover iteration. So this is how I can enhance the probability of finding my x2. And now the question is one enough? One Grover iteration enough? Depends. In general, no. So you start with the vector S, again, arbitrarily close to the loose state, and then you apply one Grover iteration, so you rotate by 2 theta. Then you keep applying another Grover iteration, and then you still rotate, and then you keep going. at some point, you basically, you reach the point where you maximize the winning probability. So where you get close to the win state. And that's exactly the point where you want to stop, because it means that you are very close to finding the win state. So now what happens? Let's say that I don't know that I have to stop and I continue playing. If I continue applying Grover, what happens is that this vector gets again pushed, but now it gets rotated farther away from the win state. So what does this mean? It means that if I start with S, I increase the probability of finding the win state only when I'm here. And then if I keep rotating, I start again decreasing the probability of finding my win state. So this is what I don't want to do. And then if I keep going, what I find is that, so here I again minimize the probability. And then if I keep going, again, I start to maximize the probability. So it's very interesting. You really have these fluctuations in the winning probability when you apply the Grover search. So you want to be able to stop as soon as you maximize the winning probability. And how many steps do you need to maximize the winning probability? And this is actually so what I told you before. So you need square root of n, the order of square root of n steps to find the winning state. And but I thought it might be maybe interesting for you to see why we get this. So what we can do is that we can assume that we have a large n. So it means that, so many elements. It means that the state S is quite close to the loose state. So I'm not in a very good position in the beginning. Now what I want to do, I want to go to the win state. So I want to impose that, so my initial angle plus all this rotation give me pi over 2. So I have to impose the theta plus a certain number k times 2 theta, give me pi over 2. From here, what you have to do is you want to extract this k, which is the number of iterations you need to play until you reach the winning probability. How do you do that? Again, you have to do the math. If you're familiar with this notation, this is for sure easy for you to see why we get this result, but actually it does not really matter. So if you start with theta, you can see that this approximates 1 over square root of n, where n is the number of elements. So now, once you have theta, then you can find k, and k is approximately pi over 4 times the square root of n. And this is exactly why you get the quadratic speed up in the Grover algorithm. Okay, so you need the order of square root of n trials to maximize this winning probability. Okay, so this was the Grover algorithm. I really hope this was clear enough, because as I said, it's really important. So let's now go back to reinforcement learning, and let's see how we can apply this algorithm to the reinforcement learning framework. So just to recap what I said before, the agent can use this algorithm to find the winning states that are, in this case, the correct actions faster, thanks to the use of quantum mechanics. So now what can we do? Exactly the same thing that we did when I talked about the Grover algorithm. You find, so you indicate the target element, which is the correct action. For example, again, the robot going right to find the exit. That you indicated by a 1 state. Here, the subscript A stands for actions. Okay, so this is the 1 action and this is the correct state. And then you encode all the other elements, so all the wrong actions. This is, remember, this is the state orthogonal now to the target element. You use a 0 to identify them. So it is exactly what I've talked about so far. So now you have the initial state S. You can now prepare this quantum superposition as a superposition of all the elements that you have, which in this case are grouped into winning elements and losing elements. Okay. So you can prepare the winning element with a certain arbitrary probability epsilon. And this is again what you have in this sketch. So you have 1 and 0, so the winning action and the losing and all the losing actions, and an arbitrary superposition of all of them. All right, so this is how you represent it. But now the question is, so far so good, but this was mainly a theory talk so far, but I'm an experimentalist, and I would ask myself now, how do I experimentally encode, first of all, the 1 and 0 states, and also how do I create a quantum superposition? So how do I create this initial state? So remember that again, if you take the example of the robot going left or right, having this superposition, it means that now, well, I mean, the robot is in a superposition of having gone left and right. It's probably not easy to understand intuitively, but I mean, that's exactly the point of quantum mechanics. So now how do I experimentally encode this? So again, as you might have noticed what I said, the state S is a qubit. And we, at least in our group, of course, there's many other platforms that implement this in a different way, but we do this using single photons. And one way that we use to encode this is we use a tunable beam splitter. Now, again, I don't know how many of you are familiar or remember the concept, the idea of the Mach-Zehnder interferometer. So if you remember, the Mach-Zehnder interferometer is formed by these white lines, and this theta here is the phase that I can tune to change the output distribution at the end. But if you're not familiar with this idea, it does not matter. So just consider this device as a tunable beam splitter. What is a beam splitter? It's just a device that can split the light, for example, in the upper mode or in the bottom mode. Okay, so it can be, for example, 50-50. In this case of the figure, it's actually keeping the single photon here in the 0 state. Yeah, this I didn't say, but so the upper mode and the bottom mode, they are our states 0 and 1. So now if we input a photon from here and we tune the phase theta, we can tune it to still have the photon at the end of the circuit in the same special mode, which is the state 0. And this corresponds to the implementation of an identity gate. But now what I can also do, I can now tune my phase to now route the photon downwards. So now I'm going from 0 to a 1. It means that I'm swapping the special modes of the photons. So in this case, I'm implementing a swap gate. And this I can show you just maybe to give you an idea that this is exactly how it is in reality. So this is a video that I took, sorry for the low quality, but I was coupling light in a waveguide, which is, yeah, I mean, it's a guide where light can propagate. And as you can see here, this is exactly the beam splitter I'm talking about. So here I was inputting the light from the bottom mode. And as you can see, I was switching now the phase theta to do like either identity or swap. So you see that the light now gets swapped. All right, so, and this is the main idea of how we treat the 0 and 1 state. Now, again, it's straightforward to then understand that if we want to create a superposition of photons, then what we do is we tune theta such that we have an arbitrary superposition of 0 and 1. Since you cannot divide, you cannot split the photon, in the end, the photon will end up in the mode 0 or in the mode 1 with some probability alpha and beta. So again, this is the state of a qubit. So you have the photon in a quantum superposition of the two special modes. And yes, it's as simple as that, or at least it's extremely simple for me, but I think this is I hope this is pretty straightforward. So this is exactly how we create a qubit. Now, if you are experimentalist, but even if you're not, but anyway, if you're interested in how this looks in real life, here you can see an image that we took of a beam splitter, which is exactly, you can see here, you have the solid lines, they are the waveguides, and the light can be coupled into one of these waveguides. And this is the shape of the Mach-Zehnder. And here we have the controllable phases theta and phi. But now we don't have only one. So one is used to implement a quantum gate. But when we want to do quantum computing, we want to be able to implement more gates in a row, because we want to be able to do some computation. That means that what we have is not just one of these components, but we have, in total, we have 88. Now, I don't know if it's easy for you to see, but you have like one of this component is one tunable beam splitter. We have 88 of this, and we have 26 input modes. So we can input the light from any of these modes. And this is extremely nice. So this chip was designed at MIT a few years ago, and it's extremely small. It's like only not even 5 millimeters long, the part that you can play with. Really, this is really new technology. It's extremely small with a lot of tunable components on it. So, and this is exactly now, this is our platform that we use to now implement quantum computation, and in particular that we use to implement this reinforcement learning protocol with our photons. So let's now see in more detail. So what you see here, this is the only portion of the chip. So it includes only 4 special modes and these many beam split. So this is again a beam splitter, each of them, what I showed you before. And now let's see how we can implement this reinforcement learning algorithm. So we can divide ideally the chip into 3 regions. The first one we say is the agent. The second one is the environment, and then the third one is the agent again. So now let's say that the agent. So here you have to be really quite careful with the labels here. So if you notice in the beginning here, you have 0A and 1A. So those are my losing and winning actions, and they correspond to two distinct special modes. So I input a photon from the 0 state, and what I do with this beam splitter, so with this U preparation, I can create this superposition S. So now, as you can see, this is like the yellow path. So the photon is now in a quantum superposition of the upper and the bottom modes. And as you can see, it means that it's now in a quantum superposition of the 0 state and the 1 state. And so this is exactly how we create the initial superposition, this vector here, that we need to then implement Grover. Okay, then what I didn't talk about, I did not talk about the reward, because of course the agent needs a reward to learn, so to increase the probability of performing well. So we use another qubit to encode the reward, and you can see it here in the labels. So you have like 1R and 0R. So R stands for reward. And so what we do here, we can then use these other 2 beam splitters here to now put both the rewards again in a quantum superposition. I'm not sure this is probably confusing if you're not very familiar with this, but you can really see that here, like the 2 yellow lines, now if the photon is in a superposition of these 2, which means is in a superposition of reward 0 and 1, and the same is down here. So now it's also in a superposition of 0 and 1. So from 1 mode, now the photon ends up in being in a superposition of 4 modes. Okay, and this is putting the reward in a superposition is it's crucial for the implementation of the Grover algorithm. It's crucial for the implementation of the oracle. Okay, now the first step, now we want to apply the Grover step, so a Grover iteration, because we want to maximize, what we want to increase is this probability epsilon, because we want to increase the probability of having the winning action, 1. So now with the environment, we apply the oracle, which remember has this effect of flipping the initial state. And again, you cannot see it, of course, from the setup. And again, you have to trust me on that. But the effect of this oracle, which is in the end, is a swap gate, has again the effect of flipping the sign of only the winning action. So now the environment applies the oracle. So the environment identifies the winning action, and it goes back it sends everything back to the agent. The superpositions of the reward is undone, and at the end, the agent can apply now the reflection. to complete the Grover step. And so again, you see it here from the sketch. Now we're moving closer to the 1 state. So what does this mean? It means that the probability of finding the action 1 is now increased compared to the initial state. And so this is exactly what I've talked about so far. This is exactly the application of the Grover algorithm. Okay, so I use it to enhance the probability of finding my winning state. Now, so far so good, but there is actually a problem. And the problem is that now the photon ends up in both of these waveguides. But if you see, both of these waveguides correspond to these 2 states, 0, 0 and 1, 0. So as you can see, the reward is the same state. So it means that if I now put 2 single photon detectors at the end, and I want to detect with these 2 probabilities if the photon is in D2 or in D1, actually, I can find out which action, I can measure the action, so I can find 1 or 0, but actually this does not tell anything to the agent because it cannot measure the reward. In principle, the agent doesn't know if 1 or 0 is the correct action. It needs a reward to learn. So now, and this is a problem because of course you need to have a reward. And this problem is fixed with classical physics this time. So we can now use a classical round. So you see the term epoch, it's a round of interaction. So we can use now what we measured to find the reward. So let's say we found now the photon with a certain probability in detector D1. What we do is we now input the photon from 0, 0, so from where we found it. And now this is the classical case. It means there is no superposition, no quantum features. So now the agent does not do superposition, does not create superpositions anymore. So this will be just a straight line. And here as well. So the photon will just go straight. Okay, and it will be detected in D1, which has the reward 0 here, which corresponds to no reward. Okay, and we'll see why, because now if we set the photon, remember here, was detected in D2, okay, which corresponds to the 1, 0 state. Now the photon is input from the 1, 0 state, because now I want to test this as well. And here it will go here. The environment, what I said before, it's just a swap gate. So the environment will just swap the mode of the photon. It means it will go, this mode will go from 0 reward to 1 reward. So this is how the environment assigns a reward to the agent. So this time I will find a photon in D3. So it means this time this corresponds to the 1 reward state. So now I have the possibility of distinguishing between reward 0 and reward 1. And this is extremely important because as soon as the agent finds a reward, now the agent can update the initial probability epsilon in the initial superposition to some other bigger probability epsilon prime. Now I can start a new round, preparing now this updated probability until this epsilon is maximized.
Valeria, may I simply say, could I simply say that I am doing, say, two-level unitary, a swap between a 2-qubit swap
Yes.
of the internal? Okay, so I mean, this is a 2-qubit operation.
Actually, it's a CNOT gate that you do here. Yeah, like you have a generalized CNOT gate that you do.
Mm-hmm.
I don't know if this is, I mean, yeah, I don't know if this is intuitive, like you see it like, yeah.
Take the second, I do not understand why you call classical the second gate. I mean, if I take this circuit and I just attach to the first one, it is simply a CNOT followed by an I-swap gate.
You mean if you take this, if you attach it, which one? So this circuit to
the first one.
Sorry, this one to this one.
No, the one of the previous slide.
Okay, yeah. Yeah, well, yeah, actually, that what you would do if you would have a long enough chip. Yes.
No, just for, I'm a theoretician. I don't care about chips.
Okay. I see. So, okay, I can just quickly clarify. So we just say classical because we do not use any, in this circuit, we do not use any quantum feature at all. Okay. So we do not create any superposition at any step.
Sorry, but you are making a gate between the you're making a gate between the 1A 0R and 1A 1R. But if you see it as if you see both these graphs as a transformation of the two central states, you are doing a kind of quantum gate. This is my point.
Okay. Yes, I agree. Yes, in that sense, yes. No, I completely agree with this. Yes. Okay. Yes, we needed something to somehow distinguish, because this is extremely crucial somehow. So we needed something to distinguish when the agent prepares the superposition and when it does not. And so we said when it does it, then it's a quantum it's a quantum scenario. When it does not, then it's a classical scenario. I completely agree with what you said.
Okay. I understand that. Good. Yeah. Thank
you. Okay, sure. So then I said, so that, okay, in this case, now the reward is assigned. Yeah, and now, so what I said, now epsilon can be updated. And this means that now it's a little bit more likely that the agent now sends the photon downwards, so to the one state, and then it continues like that until the probability epsilon is maximized. So this is what we have now. Again, exactly for this reason. So this is why we call it the hybrid agent. So we say the agent plays a quantum round and a classical test round. So it alternates between these quantum and classical rounds. And after each classical rounds, it gets a reward, it updates, and then it starts again, quantum classical, and it updates. And this is the experimental result that you can see in this plot. So now if you plot the average reward eta versus the number of I mean, it's even epochs because we're only plotting the quantum, but it does not matter at all. So we're now playing, this is many agents playing one after the other. And so in the end, we get an average reward here. So what you see is that if we now play this quantum strategy of alternating between quantum and classical, which is the blue curve, you see that here in the beginning, it's much faster than in the classical strategy. So you see here that the curve is more steep. But you may also notice that there is a big problem. And the problem is that there is a drop of this average reward as soon as this probability epsilon reaches a certain number of 0.396. But that doesn't matter. So as soon as it reaches a certain number, it starts to go down again. And why does this happen? This is exactly what I said before in the Grover algorithm, that you don't want to overshoot. You want to play and you want to stop when you find what you're looking for. If you keep playing, then you again move away from the winning state. And this is exactly this effect that you can see here. So now it goes down again. So it's like de-learning, I mean, if you can say that. But so you want a way to fix that. And the way to fix that is again using classical physics. So the agent can alternate between quantum and classical rounds only until it reaches the maximum of the curve. And then as soon as it reaches the maximum, then it starts playing classically. In this way, you avoid the drop. So here you have in the beginning until here, you have this quantum classical alternation. And from this point on, then you have only a classical strategy. And in this way, you're always able to outperform a completely classical strategy because you're always above the classical curve. All right, and so if you see now, if you define the learning time as the number of rounds of epochs that you need to achieve a certain probability epsilon, which should of course be smaller than the switching probability, because you see the advantage only in this region here. So we took, for example, epsilon 0.37, and we found that you would need classically 270 rounds, and quantum mechanically you need, if you play these Grover steps, you need 100 rounds. So in this case, you could reach a 63% reduction in the learning time compared to the fully classical case. So this is the way. Now, the take-home message. So I hope this was clear even for people who are not really from this field. So, but I think what is important to remember about this is that, first of all, in reinforcement learning, it's possible to quantize agent and environment by allowing them to create and to send quantum states in quantum superposition, because this allows the implementation of the Grover algorithm. So, and with the Grover algorithm, I can find the winning actions faster. So in general, I mean, the main message is that quantum technologies can allow machines to speed up the learning process. And I mean, I would say that, of course, this field, we're still really at the beginning of understanding what this field can do. There's a lot of work going on in the field, but not only of reinforcement learning, but of artificial intelligence in general. So let's see. I'm curious to see what will happen in the next years, because at the moment it's very exciting. And with that, thanks. And that was it. I don't know if you have questions or.
Yes, thanks a lot. First of all, let's thank you for this really nice talk, very interesting and very nice presentation. Just by itself, you said a lot of things in a pretty simple way, and it's really a beautiful experiment. What I'm a bit curious to know is a bit. What is the perspective scaling? Let me say, I mean, quantum computation started with the promise of an exponential speed up. We know that Grover algorithm is not exponential speed up, and you are telling that you have a speed up in Grover algorithm, which seems to me. I mean, the initial scaling is promising, but at the end, I do not see in the picture. The picture is experimentally great, and I imagine how difficult it could have been. But can you convert the final result in the prediction?
Yeah. So
large n, which is somehow it tells that you have a decisive overperforming.
Sorry, I didn't hear. Like you broke for like the last sentence.
Yes, what I said is that it's. Let me say, it seems that the algorithm, of course, it performs better, but quote, not that better.
Yes.
What happens if I increase the size? Can I think that there will be a scaling?
Yeah.
A scaling that will enlarge the difference, or will it shrink? So
Yeah.
in the limit of n going to infinity, is it very different from classic, from the not from the classical, from the standard Grover, or it is said in other words, did you find an algorithm which is in a different class with respect to Grover?
Okay, so a few points. So first of all, if you stick to this algorithm, so first of all, can I 1 second stop sharing the slides, because
yes,
or just because it's very weird to talk to a black screen. So first thing is, yes, if you stick to this algorithm, then what you can achieve at best is a quadratic speedup. What I would like to say that I did not mention here is that actually we did not even demonstrate a quadratic speedup. And this is really can do more or less at best with the current technologies. If you want to perform an arbitrary number of Grover steps, then you would need a very long chip. And we could not do this because, I mean, still like this is a very new field and this is really like what we have at the moment, right? So we were playing one step and then measuring and then another step and then measuring. So in this sense, we could not achieve a quadratic speedup, which you might achieve in theory, in principle. And I mean, with better technology in the future, there will be like super long chips, hopefully, and with a lot of modes. And of course, you can also increase the number of photons, right? So you can have this exponential advantage when you increase the number of photons. And yeah, in the end, you might be able to implement more complex learning algorithms with more actions, for example. But now the point is, I see the point. And yeah, this is not really... So you're saying, I mean, the quadratic speedup is nice, but...
No, I'm not saying that. Probably there was a I mean, I did not explain me. I mean, clearly, Grover achieves a quadratic good. It is okay. What I'm interested in is outperforming Grover.
Yes. So there are other algorithms that have been that can achieve actually an exponential speedup. Mm-hmm. Yes, but this is just still at the very theoretical level. Of course, it's still.
May you can achieve exponential. May you repeat, please, the sentence I didn't get?
Yeah, so there's some papers that talk about the idea of achieving an exponential speedup, for example. But this is, I mean, I think it will be possible in the future. I don't know, but this is still being currently investigated. This is still at the theoretical level, and so it was already hard to translate this, like this idea of using Grover to an experimental quantum platform. I'm sure that there will be new developments in the future, so you can outperform this. There are even some other algorithms that do not outperform the quadratic speedup, but what they do is that they avoid the drop in the Grover search. Mm-hmm. So they don't use the Grover search, but they used another algorithm which is called fixed point algorithm, which allows to still achieve an advantage, and you don't even have to then switch to classical, because it will just then like go always up without going down. So yes, there's a lot of interesting ideas that are currently now being developed. We'll see. I'm curious.
But I think my question is, I mean, you are giving interesting answers. But in the meanwhile, I'm trying to formulate better my question. Let's go a little bit a step behind. We know that problems are classified with the complexity classes, and classical complexity classes may change. For instance, if you have a deterministic or a probabilistic algorithm. I asked to myself, is a quantum machine learning, is a quantum reinforcement learning algorithm something that may achieve this kind of advantage over a quantum algorithm? So I'm not telling. I mean, I'm asking if, and what I see from your result, which is a fantastic experimental result, is that if I want to if I want to train a perfect object, I have to put resources which are comparable with the standard algorithm. I do not have a relevant outperforming. I have a relevant outperforming if I want to do something, but if I want to do the best, then it seems to me that I do not have a great outperforming. Is there any study that says that maybe in some instances one can find a big outperforming of quantum machine learning algorithm over quantum algorithms?
Okay, I see. So my answer is not that I know of. So what at least what I've seen, it's always like quantum algorithms trying to outperform classical algorithms. I mean, I'm sure there's studies for sure. I do not know, like in the specifics, if someone has investigated this actually, because like to me this sounds like. So what we did, we took like the best that the theory could provide us that we could also apply to the experiments. So the answer is, I mean, certainly, like it's an interesting question. Maybe, I mean, I'm sure the theorists are probably investigating this as well.
Sure.
I mean, and yeah, and they're trying to because they're really trying to push, you know, like the limits of what you can do at best, and also because if you talk about quantum machine learning, because this is like the reinforcement learning field, but and again, like I'm not an expert in supervised and unsupervised learning. But I know that there's a lot of quantum algorithms, but still, like, you know, trying to outperform classical algorithms also in that field. So it is. I see.
I was as a chairman, I was really unfair because I was enthusiastic of your talk, and I didn't see that there are many hands raised, and people have to make question, and I even didn't check the order. So please, one of the first person raising hands, it's allowed.
Yes, that's me. Thanks for the talk. Actually, it was also clear for me. I'm very not familiar, so I'll probably ask really most likely very easy questions, and I hope also quite fast. So one thing is, okay, you said this is going to work only for single photons. In the experiment, how do you make sure that you inject a single photon? Like, really, how do you do that? And what's the source also? So
this works actually also if you do it with coherent light, just with injecting a laser. But then what you get, then it's, so the concept is different, because then at the end, so I just want to clarify that then at the end you have the light in both output ports. You don't have this with photons. And then so you have to measure the probability distribution and sample from that in order to find
the transmission, basically.
Yeah, if you want to do it with classical light, but you have one step more, because you have to measure the output, sample from the distribution, and then start again a new round. With single photons, you get that for free already with the measurement. But okay, yeah, that's the advantage. But yeah.
Okay. Then, yeah, sorry.
No, sorry. What was your question?
No, how do you? What's the source that you use? No, okay, probably use a laser.
Yeah, so we use a laser and we pump a single photon, a nonlinear crystal. We use it's called periodically pulled KTP, but it's basically a nonlinear crystal. And when you shine laser light onto this crystal, then what happens is that a nonlinear process that creates a pair of single photons out of the crystal. Okay. Which really have like single photon statistics, and then and so then you can use these two photons to do the computation. So yeah, you really have to make sure that you have you create single photons with this process. You couple them into optical fibers, and then you direct them to the chip.
Okay, then I have another two small questions. I've seen in the plot of that the axis of the epochs was actually going to 400, but then you said that there's only like 88 Mach Zehnder. So I was wondering what's the deal? You re-inject the light, or how does that work?
No, you don't have to consider the. So one round, one epoch is one full computation in the whole depth of the chip.
Okay.
So it's like that is one. And then you redo it again, like the second round, and you go again through the whole chip, and then is your second.
Okay.
And then you continue. That's why. So you can have an arbitrary number of rounds.
Okay.
It does not depend on the depth.
Okay. Then very last question. You mentioned that the reward was about to oscillate, because at a certain point you overshoot and then you come back again. but I didn't see that in the plot. So is this just that the scale is not enough, or it was about to go up again, or?
No, actually, no. Okay, that's a very good question. It's a very smart question. No, that does not happen. And I'm sorry if this will be super confusing, but this does not happen because in between every Grover step, you also have an update. So every time you find a reward. So you play Grover until you maximize the winning probability. And that's where you every time get a reward. But now if you keep playing, now you start going down. But then at some point, you will approach the lose axis. But when you start to approach the lose axis, you don't find any reward because that's not the action that you want to find. And if you don't find any reward, there cannot be an update.
Okay.
So it means that if there is not an update, then it can just go down and then stay constant.
You get stuck. Okay.
You get stuck. Like you cannot go up again.
Okay.
That's a good question.
Points.
Thanks a lot.
You have 2 fixed points, basically.
Yes. Yes.
All right. Thanks. I'll leave the floor for others. Thanks.
Yeah. Also, maybe a stupid question because I'm not familiar with reinforcement learning. So just understand. So in the example, you use 1 qubit to encode the action, right? So I didn't understand. So like the qubit encode only the action for the step, for one step, or it encodes the full action strategy. So for example, if you have multiple qubits, you will have 1, 1, 1, so always left or whatever. So
no, sorry. Yeah.
No, that was it. So you can go ahead.
Yeah, so if you have multiple qubits, actually that would be the idea that if you have multiple, I did not talk about this. I just said actions. Actually, this protocol, in this protocol, it's not just one action like left or right, but actually one like staying up in the upper mode or in the bottom mode is actually theoretically a sequence of actions. Now, if you want to encode now this sequence of actions, let's say you have the dimension of your action space is n, and the length of the sequence is L, then what you can do, you can use n to the L, you can use multiple qubits to encode this. Okay, but in this case, for example, in the simple case that we showed, then you have only like up or down. Yeah, that's just like 1 qubit encodes, yes, like performing the action.
Okay, so it's not only the next action is the full strategy that your agent will follow.
Yes.
Okay.
Yes.
But then another question comes out of this. Like if with the Grover you find the best rewarded strategy, why then you need continue learning? Like couldn't you stop and use always that strategy? Or is it this what you do, right? Okay.
Yes, we stop at the best peak. In principle, yes, you could do that, but you really want to then go up, right? Because then if you stop at the peak, then you reach like less than 0.5 average reward. So it's still not really the best.
Okay, so with Grover, you still didn't really find the best.
Exactly.
So you need the classical.
Yeah, so then you still need the classical to still increase it.
Oh, perfect, thanks. Now I understand.
Cool.
Okay, I have a really quick question. First of all, thanks for the talk. It was really great, and I understand most of it, so it was really great.
Good.
I was wondering, like device-wise, there is a roadmap for implementation of such chip in a more complex environment, such a device. Will you plan to use it in a more complex situation?
You mean to implement this algorithm in a more complex situation, or?
You showed us a chip that was the setup for the experiment.
Yeah.
Is there a time frame that you plan to maybe to use such a design in a more complex device?
I see. I mean, not at the moment that we have, but I mean, not with this specific algorithm. But I know that actually exactly this type of platforms now, because they're fully tunable, so they're actually very suitable for this learning algorithm where you need always an update of the underlying circuit, right? So yes, there's many, like now there's also the idea of using these chips for implementing neural networks, for example, right? So there's a lot of ideas of implementing this type of algorithms. Also for, yeah, I mean, any artificial intelligence task, they do like supervised learning trainings, neural networks, and stuff like that. So yes, it's one of the first demonstrations using this type of setups, and they're actually working. They implemented deep learning also with this setup, like some voice recognition. That was very cool. So yeah, I mean, people are working on that.
Could be the basis for a future neural engine. So
it could be, but the problem is that so because this is just linear optics, and if you want to implement a neural network, you also need nonlinearities, like at every hidden layer, and that's a problem that people are trying to overcome, either with new chip design where they're also inserting like really physically like layers of nonlinearities, for example.
Okay.
Yeah, this is still, I mean, people are designing that, but yeah.
Okay, thank you.
Okay, Luigi?
Yes. Hello. Yes. So one question is that usually in reinforcement learning, the action that the agent takes depends on the state or observation or percept, as you call it, I think, from the environment. I didn't understand if this is implemented in this algorithm, and if it is, how, and if it is not implemented, how would you implement it?
Yeah, good point. I did not talk about this. Basically because no, it's not implemented. And actually, there is not even a need for the type of algorithm that we have to implement this. And the answer is because we consider environment types that are deterministic. In deterministic environments, it means that the response of the environment, so the percept that the environment sends, is always fixed. It's like playing, I don't know, the game of chess. So that is always fixed. And if it's fixed, it means it's completely determined by the action and the reward. So there is no need to implement that. So in this specific type of experiment.
But I mean, also in chess, the action that you take depends on the state of the board.
Yes, but then the state, like at every round, that state depends on the action, right? So it's always whether there's a reward or not.
And my question is, the action that the agent takes also depends on the state before.
Yes, so in this case, we use a fictitious, let's say, percept that we call percept S0, which is basically what we need to start the round. That's how we implement it. I mean, then it's not a real implementation, right? So we say, okay, let's say that now we have this percept S0. This gives us the start to start the round. This is the first one, and we only need to define this one, because then after every action, then the percept is always defined because it's a deterministic type of game. So I don't know if this is clear. So but you really don't need to. You have one. You have the initial one that tells you, well, okay, you can start the game, and that's it. You do not need to encode the precepts. And in this type, at least I don't see it at the moment. Like in this type of implementations, I don't even see. I mean, maybe I have to think about it, but I don't see how you would implement the state of the environment. But because in this case, it is really not necessary. Then, I mean, there might be other algorithms that will exploit this. Actually, there was also the algorithm that I showed when the agent is classical, but the environment is quantum, that they demonstrated that it's possible to design new quantum experiments. In that case, for example, they had the percept. There was the optical table, for example. So it really depends on the type of algorithms that you wanted to implement.
Okay, thank you.
Sorry, just to understand. So, but if you pass the full strategy, isn't the state or whatever is this? I mean, I know that it's hard to define state in this case, but isn't this information kind of implicitly encoded into the Grover's oracle? Because then the Grover oracle knows how to rotate the state into the reward, right?
Yes, exactly.
So it kind of, but then the example of chess maybe doesn't really work in this case, or?
No. That was just to mention deterministic environments. No, it does not work.
Because otherwise, yeah.
Yeah, sure.
Okay. Are there? Okay. Just. Attivo il volume. Va bene. Okay, done. Okay, thank you. So, are there any questions? Any more questions? Ragazzi? No. Okay, so if there are not other questions, we thank Valeria again. Again, thank you for the nice talk, and hopefully you can come in presence to make another talk.
I mean, when the restrictions will be lifted, if it's possible to come again, I would be actually very happy to come visit. So
yeah. Are you in Vienna now?
I'm in Vienna. Yes. Yeah. I will. Yeah, because I will finish. I will get hopefully my PhD next month.
Okay.
Yeah, and then I hope I can come back home.
So it will be summer at least.
Yeah, summer at least. Yeah, we'll see.
Allora, in bocca al lupo, allora.
Happy. Thanks all for listening. And
Thank you again. Bye.
Thank you so much.
Thank you. Bye bye.
Thank you. Bye.
Ciao.
Ciao,
Thank
Vale.
you. Bye.
Pino, auguri,
Ah, grazie. Ciao a tutti.